Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on September 17th, 2025, which means it dropped just yesterday. The standout claim is a single transformer called GPhyT that learns governing dynamics from short context and then simulates many kinds of physics, showing superior accuracy over specialized models by up to 29 times and generalizing zero-shot to new systems. The paper is titled Towards a Physics Foundation Model, and the implications for model training are quite significant. In short, a neural differentiator paired with a numerical integrator delivers stable 50-step rollouts and adapts across boundary conditions without retraining. On X, a hacker news bot shares the archive link with a headline matching the title, pointing readers to a discussion thread and the paper page. Engagement looks minimal, with no visible like or repost counts. Alright, the previous figure introduced the motivation. Figure 1 now lays out the pipeline. A stack of past fields becomes spatiotemporal patches, which the tokenizer and spatiotemporal transformer process to predict the time derivative, and a numerical integrator advances the state. The left panel illustrates tubelet patches taken from multiple timesteps, which provide context so the model can infer dynamics. The right panel sketches a transformer layer with layer norm, spatiotemporal attention, and a multilayer perceptron. So the previous figure sketched the model pipeline. Table 1 summarizes the training corpus, which spans 8 simulation families, with trajectories, time steps, snapshots, and counted unique samples. The mix covers shear flow, Rayleigh-Benard, Euler, obstacle and thermal flows, a second Rayleigh-Benard set, and 2-phase porous flow, so boundary conditions and scales vary widely. The totals matters because scale drives generalization. Over 2.4 million snapshots expand to more than 71 million unique prompt target pairs through time increment and flip augmentations. The origin column notes which sets came from the well versus custom runs. Okay, the previous figure outlined the dataset scale. Figure 2 presents average and median mean squared error across all test sets, with lower bars indicating better accuracy. The black bars mark average error, and the hatched gray bars mark median error, which highlights robustness across tasks. GPhyT variants drop the median error dramatically versus FNO and UNet, so a small GPhyT with roughly 9 million parameters already beats the larger baselines. Larger GPhyT models continue to reduce median error, which signals favorable scaling. So, the previous figure highlighted model accuracy trends. Table 2 reports zero-shot means squared error for in-context learning across boundary changes and entirely new physics. Obstacle flow shows small errors for symmetric and periodic cases, and the open boundary stays close, which indicates boundary inference from prompts. Euler remains similar between periodic known and open new, reinforcing that point. The toughest tests, turbulent layer and supersonic, have higher errors, yet the values still indicate physically plausible forecasts rather than collapse. Well, the previous figure compared overall errors. Table 3 now reports averaged mean squared error per dataset for single-step prediction. The table shows that GPhyT variants consistently beat FNO and UNet, with GPhyT-XL achieving the lowest average at 3.46e-3. Obstacle and shear flows post especially small errors, while Rayleigh-Benard and Euler remain harder because shocks and sharp gradients amplify mistakes. The small GPhyT already undercuts the larger baselines, so scaling mainly refines an existing lead. Wrapping up, 2 takeaways stand out. First, a single spatiotemporal transformer with a neural differentiator and a simple forward Euler integrator matches or beats specialized solvers across many systems. Second, short in-context prompts let it generalize zero-shot while staying stable over long rollouts. The broader implication is democratized, faster simulation. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.